The second part is controller design. So to design the controller, first you draw the diagram and find the closed loop transfer function. So with the system modeling, we found the open loop transfer function. So here you have to find the closed loop. Identify system order, which is basically, is it first order or is it second order? And rearrange it to fit the general form. So you need to get your transfer function so it looks like either this one for first order or this one for second order. And then you can solve for the KP, KD, and KI, which would basically take the place of the C's here based on your desired system parameters. So C is not going to necessarily equal K, but it'll be in this form, and you'll see once you actually rearrange the stuff in the problem, how to get K. And so in the denominator, you're going to use coefficient matching. So that means that you have your system in a form, you want the coefficient of the S squared term, or the highest order S term, that coefficient should be 1. So you'll have to rearrange your transfer function so that happens. And then you can match the S coefficient and then the nothing coefficient and solve out for KP and KD. So you rearrange the open loop transfer function, put it into this form, solve for the control constants. There's an example with like all of the algebra worked out in the notes, but we will do here for the mass spring damper. So step 1, we draw the control system diagram. So we have the plant, which is the mass spring damper. And then we have the controller, which is KP plus KD times S. We didn't use a KI here because it would make the math a nightmare. So we'll just go with KP plus KDS. You always have KP by itself, and then KD is going to be times S, because this one's the derivative controller, so it acts on the derivative variable. This is the proportional controller, so it just acts by itself. So then we get the closed loop transfer function. So that would be output over input. You do some algebra, get this formula, then you put in the numbers. So you can see here that S squared has an M in the front. But we need to get this into the general form. We need to get rid of that M in the front. So basically, we just divide everything else by M. So identify system order. We saw it second order. We rearranged it to fit. So second order, then when we divide everything by M, we get nothing in front of this. Really, it would just be a 1. And then we have these coefficients. So if we know values for zeta and omega n, we can figure out what KD and KP have to be by setting that equal to that. And then we set this equal to this. So on a homework problem, I'll give you everything except KD and KP. So you'll know omega n, you'll know zeta, you'll know B, M, K, and then you can just solve out for KP and KD using coefficient matching. Now there is a homework problem that is almost exactly this thing. So I just give you the numbers. So M, B, and K, these are going to be given in the problem, or you measure them from your actual robot. Like you weigh it, figure out what M is, stuff like that. Zeta and omega n, you always choose. That's part of your designing the controller. So if you want no vibration, make zeta be 1. And then generally omega n is small, because if it's really high, like if it's more than 10, your system is just like, it's just too hard to catch it. There's really no reason to make it very high. Then you can solve for the K's.